Okay, hello everyone. Welcome to our monthly COFFIES Seminar, and today we have a special treat. So this month's NASA Heliophysics Big Year's theme is performance art, and to add a little bit of sweetener to our monthly seminar, we are having a poetry reading, and we invite David Hassler from Kent State University, who is director of the Wake Poetry Center, and Aimee Norton from Stanford University, who is part of our COFFIES Center. So we invite them to do a 10 minutes poetry reading, and then we will go to Catherine's seminar. So welcome, David and Aimee. David will go first.
Thank you. Thank you, Rizu. Hello, everybody. I'm David Hassler, Executive Director at the Wake Poetry Center. And it's been a thrill to collaborate with Dr. Aimee Norton on building an interactive website for the 2024 total solar eclipse, a community poem website where people can read a model poem that I wrote, which I'll read in a minute, and then choose a prompt to share their own creative expression, their own sense of awe and wonder at their experience of the eclipse. And to do that, I'm going to do share my screen and click on the website here. And essentially, it's a tool that we've been developing at the Wake Poetry Center as part of our Poets for Science initiative, which was founded initially by Jane Hirschfield as an idea in 2017 to bring a poetry presence to the original March for Science on the Washington Mall in 2017. She reached out to me. We worked with our design team, and at that time, she curated 24 poems about science, which we designed as banners and brought them to the National Mall. Since then, this has evolved. And in fact, Aimee Norton reached out just through the Poets for Science website. We've presented and built community poems for the American Geophysical Union for a couple of years now. And she said, hey, I'm a poet and a scientist and a poet. And this was leading up to the total eclipse. And I asked her to collaborate with us. So building the content for this website was exciting. And as I mentioned, I'm going to read this poem that I wrote to inspire others to share their own reflections in response to the eclipse. Once they do that, they can then pin their poem onto a map. And this is expandable. You can move it around. And when you click an icon, you see the poem or reflection that person wrote. And we built it along the path of totality. You can also click grid and view over 450 responses from around the country. And people could upload photos to go with their poem, or they could write on an actual card that we printed and distributed here that has the poem, a design on one side, and then the poem on the other with space to write and draw. So essentially, it gave people an opportunity to both reflect through language or through drawing. And so I'd like to read my poem, and then I'm going to ask Dr. Aimee Norton to read some of the ones that were contributed to the website as well. So this is the poem, Shared Sky, and I should say, wonderful and brilliant editing advice from Aimee Norton to workshop this model poem of mine that took quite some time to write, having never seen an eclipse myself, but have simply read about it and activated my imagination. I should say that Jane Hirschfield has a beautiful quote. She says, poetry and science are not opposites, but allies. And the microscope and the metaphor are both instruments of discovery. So in that sense, and here with an eclipse, you could say the telescope, the lens through which we view and the lens of language through which we make metaphor and meaning are both instruments of discovery. Shared Sky. Sun and moon, bring us together, all of us, sky watchers, stargazers, staring up, dreaming out beyond ourselves. Let us wonder at our clockwork universe and witness your magical vanishing act. We want to stand in the sweet spot, aligned on the path of totality, to watch as the moon's umbra flies from Mazatlan to Newfoundland, over Texas, Ohio, and Maine, gathering our homes, schools, farmlands, and rapt, upturned faces. We want to converge with you, disappear for a moment, crowned with a gleaming, evanescent corona. What diamond of insight can be revealed as the moon nibbles at the sun's edge while metallic liquid light swims about, fraying the corners of our blankets? What can we see in the dark? We humans are here on Earth to gawk, to bear witness to the spectacular. Teach us, sun and moon, to live in alignment with each other. Remind us our hearts are small cousins of you, our home star, rhythmically pulsing, expanding and contracting. Guide us in your cosmic dance. Pull us together along a shared path to whoop and cheer at your beauty.
That was awesome.
So Aimee.
Oh, okay, to me. All right. So thank you so much. That was really amazing. And for those of you that don't know, David does have an insight into solar physics because he is the brother of Don Hassler. I think most of you know that. So it's a great combination right there. So yeah, I think that this project is amazing. I'll be really brief here. So so many of our experiences in our life, words aren't put to them. So, you know, we have a huge proportion of our lives lived without any words that are describing what we're experiencing. And poetry is, I'm a big fan of poetry because it provides an opportunity for us to try to express those sort of depths and subtleties of our experiences that aren't easily conveyed in our normal talking, you know, with each other language. So Shared Sky is this project that allows anyone who wanted to witness or tried to witness the eclipse to do that, to put into words their sort of experience that is, as you know, who have seen an eclipse, it's pretty hard to put into words. So I just wanted to share a few of the things. I know we're right at the 10 minutes, but hopefully I can do this quickly. Let's see, share. And I was going to start with one of the youngest here, where somebody's, can you see this? I don't know if you can, but somebody's parent wrote down what they obviously prompted their child, who's 4 years old, Ranja, and then wrote down what the kid said. And I love some of this. And so the kid says, "What are you doing this summer, sun and moon? I hope that you, sun and moon, think the same as I think. I'm thinking I like the sun. I like the shade of you." And then also, sun and moon, I wish you good luck. It has been a very long time since you were babies. I am almost a big kid like you, sun and moon. So you get this sense of like the kid anthropomorphizing, thinking about how he must have, or he or she must have asked their parent how old the sun and moon are, something like that. But I thought that was amazing. And then some of the really nice drawings that are included are, well, like this one, the train and the car race an eclipse, which I just think is a classic kid, you know, like drawing. And then there's one really beautiful one from somebody named Stephanie that I'm looking for right now. Oh, this one. I don't know if you can see it, but it says, "The sun brings us together in a shared smile. The sun is a friend for everyone." I can't really read it, actually. "The sun is golden honey dripping down a spoon. And it's a friend for all of us," or something like that. And I just love the drawing there as well. And then some people just put in the most amazing art. Let's see. Like this one here, I think is amazing, this drawing of the eclipse. And maybe I'll just read one more since we're a little bit over our limit, and then we'll just call it a day for poetry. I think this one, the scientists will like it. It's called Occultation by Samuel Carter. And it says it's a strange thing. The hiding of that which is always visible draws the attention of thousands. But the hiding of that hiding threatens to disappoint them all, which I think is really clever. So yet neither hiding is total. The darkness will not be total, nor will it be undetectable. Nothing is ever truly hidden, nor is it truly visible either. So anyway, there's a lot of contributions. If you want to peruse this site, I encourage you to do so. And I think that this has really engaged the public in a way, in a unique way, around solar physics. So I'm really thankful that David Hassler's worked and the Wick Poetry Center has worked with those amazing graphics as well. So thank you. I'm trying to stop sharing screen here. Okay. So
Thank you. I realized I was muted. Sorry. Thank you to David and Aimee. Wonderful work. And it's really interesting to see this little kids drawing. That's very fun and creative. So, okay, we can then have our time for some science. And we are going to have a seminar from Catherine Blume. So let me introduce our speaker today. So Catherine Blume is a graduate student at the University of Colorado Boulder. She did her undergrad at Princeton University and is now in the 4th year of her PhD, where she is advised by Brad Hindman. She is currently interested in all things inertial waves, particularly in the solar interior. By developing a better understanding of the theory of inertial oscillations in a solar-like environment, she hopes to one day use these waves to do heliosysmology. So let's welcome Catherine again, and we are looking forward to her talk. Catherine, are you able to?
Sorry, yes, hello. I just had to find the Can you hear me?
Yes, now. It broke
Okay.
a little minute ago.
Okay, great. Hopefully my internet will hang on for this talk. Yeah, so anyway, thank you so much for having me. I really enjoyed all of the poetry. Clearly, I need to turn this talk into an epic poem or something like that to make it make it more fun. But yes, as the introduction indicates, this talk is all about inertial waves in the solar interior specifically. I've been running fluid simulations, nonlinear fluid simulations of the solar interior for a while now, and we've seen a lot of different inertial waves in them. So this talk is going to be about all of the different kinds of waves that we see and how they are related to each other, and it will give us a better understanding of the various observations that we've seen over the past couple of years. So we'll start at the beginning, ease into it. Everything you need to know about the solar interior for the purposes of this presentation. As we all know, we've got a nuclear core surrounded by a shell where the primary form of energy transport is radiation, so it's the radiative interior. And this is surrounded by an outer shell where the primary form of energy transport is convection. So that's the convection zone. The radiative interior is convectively stable and the convection zone is convectively unstable. So I will occasionally refer to those as the stable region and unstable region in this talk. On the right, we have the interior rotation profile of the sun. The outer region is the convection zone. And as you can see, it's rotating faster at the equator than at the poles. So it's rotating differentially. And this here is the upper bit of the radiative interior. And as you can see, it's rotating at basically the same rate everywhere in latitude. So it's rotating rigidly or rotating like a solid body. And because we have a differentially rotating area and a rigidly rotating area, there's going to be a transition region between the two. That's the fluid shear layer called the tachocline. Lots of interesting physics happens there. And we'll come back to this plot later. So now, what is an inertial wave? This is a slightly complicated question because a lot of different fields have been thinking about inertial waves for a while, and all of them have different nomenclatures. So for me, an inertial oscillation is any wave where the restoring force is the Coriolis force. But it also refers to a very specific kind of wave in that category, and we'll touch on that at the end. But for now, these are waves that are very much a product of rotation, and they occur on all kinds of big, round, rotating fluid objects in the universe. they are very important and very present on Earth. They're critical to terrestrial meteorology. The kind of canonical example of inertial oscillation are the wiggles of the jet stream. We'll get to that later. But they've also been seen on Jupiter, maybe on Saturn, and most importantly, for the purposes of this presentation, inertial waves have been seen on the sun as of 2017, 2018. And that's what we're going to be talking about today. So the second big point, why should you care about these things? There are two.
Catherine, your the sound was frozen for a minute or so. Can you just repeat your last sentences?
I wonder, Catherine, even though we love to see your shiny, excited face, whether turning your video off might help. So far, still can't hear you, although your video is playing.
She's in France now. Because the internet is trying really hard to do that. Is she still in the room?
Am I?
We have
Hello?
you now.
Yes, we
Yes.
can hear you now.
Okay. I'm so sorry. Let's try this again. Let's see. Okay. Video off.
We are seeing your movie nicely, but we don't hear you right now.
It might just be because the movie is taking up too much bandwidth.
That is very possible. Okay. At which point, let's see.
We all seen the video. Maybe we will skip the slide and go to
Yeah,
the
we'll
next
just
and
keep
see.
on. There's a lot of videos in this talk though, so we'll see how this goes. Okay, is the third time the charm. All right. So the other big reason why you should care about inertial waves is that they could be very useful. Helioseismology has been very successful at using acoustic waves and our understanding of how acoustic waves move through various environments to back out information about the solar interior, but they do have their limitations, and so there's an interest in potentially using inertial oscillations, which are sensitive to different fluid properties and live in different regions of the sun, to do helioseismology and learn something new. So here, I have so many videos. Let's hope this works. Here is a summary of all the different modes that are kind of relevant to this talk that have been observed or modeled. So on the left here, we have what I'm calling classical Rossby waves for the purposes of this presentation, that were the first observation back in 2017, 2018. There are also high latitude modes and critical latitude modes, which I'm not going to be talking about, but I figured I would mention. We have the high frequency retrograde vorticity modes, which we'll be talking about, that were observed a couple of years ago. And then over here, we have thermal Rossby waves, which have been modeled, but not observed, which is interesting. And we also have this retrograde inertial mixed mode, which we'll talk about, that has maybe been observed, but has also shown up in simulations. So, and then at the end of the talk, we're going to talk about how all of these things over here on the right are all part of the same family of waves, and to hopefully make this diagram a little bit easier to understand. So first, I'll talk a bit about the simulation that I'm using, then we'll talk about classical Rossby waves, then we'll talk about everything else and tie it all together at the end. So first off, I am
It's the movies again.
we're just gonna, can you hear me?
Yeah, we
Okay.
can now.
I will just skip through them. Basically, I'm using the Rayleigh code. It's solves the fluid equations. It's a global model, and it produces some very pretty movies that I sadly cannot show you. The model that I'm running is solving the anelastic MHD equation. So this is the equation set that I've been throwing at a supercomputer for a lot of months. And that's all I'll say about that. And
Are you speaking or are you waiting for the video to finish?
I was wondering if you could hear me. Can you hear me now?
Yes, we can.
Fabulous. Okay. So the simulation that I've been running is courtesy of Lauren Matilsky, and he was interested in studying the tachocline, and so the simulation covers the convection zone and the upper radiative interior. And I can't play the video, but the radial velocity field looks something like this. This simulation is really fun because it has a very interesting and unique internal rotation profile. So it looks like this, and as you can see, it is qualitatively at least similar to the sun's internal rotation profile in that it has a differentially rotating convection zone and a kind of rigidly rotating radiative interior with a tachocline that is dynamically generated and sustained. And this is because a magnetic field is generating a torque that forces the radiative interior to rigidly rotate. So this is very difficult to do, and because of it, this particular simulation has a lot of interesting wave characteristics that are very applicable to the sun and what we might expect to observe and are interested in studying. So that's where this talk is going. So as a preliminary, Rayleigh is a spectral code, so I will be talking about spherical harmonics a lot, and I just want to define a quantity. So L is the harmonic number, M is the azimuthal wave number, and L minus M is the number of nodes in latitude, and I'm calling this quantity lambda because it's a very convenient quantity when we're thinking about different kinds of nodes. So for example, when you have the sectoral modes, when L equals M, in this case lambda is 0, and we don't see any nodes in latitude. If you have the tesseract modes where L doesn't equal M, in this case, lambda equals 3. And so you can count 1, 2, 3 nodes. And then over here, there are 11 of them. When lambda is even, your wave modes are equatorially symmetric. And when lambda is odd, they're equatorially antisymmetric. And a convenient way to separate out difficult results or confusing results is to separate them out by symmetry, which you will see in a few slides. So this entire presentation is full of wave spectra, so I'm going to take a minute to tell you how I've generated them. First things first, most wave spectra I'm showing are all in radial vorticity, which is a very convenient quantity when we're thinking about different kinds of inertial waves. You output that quantity at a set sample rate, run the simulation for 2 million core hours, get something that looks like this, which is our quantity in time, kind of indexed on a theta phi latitude longitude grid. Take a spherical harmonic transform, you get that information indexed in time and L and M, which is great. And then you take one giant Fourier transform over all of these spherical harmonic spectra, and you get your information indexed in terms of frequency, L and M. That's one thing too many to easily visualize. So what we do is we sum over specific L values, which looks like, for the purposes of this presentation, summing over a specific lambda. And this is similar to summing in latitude. And this gives you a set of spectra in frequency and M. So this is a big summary of the spectra that I've been generating. These are spectra in radial vorticity. In the left column, we have spectra averaged over the radiative interior. In the middle, they have been averaged over the tachocline. And on the right, they have been averaged over the convection zone. The top row has been summed over modes that are equatorially symmetric, summed over L minus M or lambda equals 0, 2, 4, or 6. And the bottom row are the equatorially antisymmetric modes that have been summed over lambda equals 1, 3, or 5. And as you can see, there are a lot of different waves, and we're going to talk about all of them. So we've got equatorial Rossby waves, a lot of them in the radiative interior on the left, although they do exist throughout. And then in the convection zone. We have thermal Rossby waves of a couple different kinds. This inertial mode here that's retrograde, and also these things, which are probably HFR modes. We'll get to that. So first up, we're going to talk about classical Rossby waves. They're also planetary waves. They're also called R modes. They've been given a lot of different names in a lot of different fields. But the general idea is that they arise from the conservation of potential vorticity. And in this geometry, which is on a spherical shell, that looks like the conservation of this quantity, which is the radial component of the absolute vorticity. This involves the radial component of your relative vorticity, which we all know and love, and then an additional component from the rotation of the actual body. So the idea, right, is that if you're standing at the pole aligned with the rotation axis, the body itself is spinning you in addition to whatever relative motion you have. Theta here is colatitude. So this is a maximum at the poles and when you're fully aligned with the rotation axis, and a minimum at the equator when you are perpendicular to the rotation axis. The general idea behind the mechanism is that because we want to keep this constant, if we displace a fluid parcel towards the pole, so we're more closely aligning it with the rotation axis, that increases this quantity. We don't want that, so it induces a vortex to spin down the parcel and reduce that quantity. Conversely, if you displace a fluid parcel towards the equator, you're further misaligning it with the rotation axis, and this will cause a vortex to increase that relative vorticity, and so on. And these vortices, of course, perturb other fluid pieces, nearby fluid parcels, and you end up getting a very large retrograde propagating wave that exists on the spherical shell. So these were observed for the first time in 2018. And this is what that observation looks like. It is similar to the spectra that I've already shown, that we've got frequency on the y-axis and m on the x-axis. And the dispersion relation that we care about for this presentation is the two-dimensional hydrodynamic solid body dispersion relation in spherical coordinates. You can make this more complicated in any number of ways. You can add differential rotation, you can add magnetism, but we only need the simple case here, despite the fact that this is a magnetic model. And specifically, this black line and what's been observed are the sectoral modes where L equals M. So this black line is equivalent to this dispersion relation when L equals M. And we'll come back to that. Finally, the eigenfunctions are very conveniently spherical harmonics, which works out nicely because this is a spectral code. The sectoral modes look like counter-rotating vortices banded around the equator. So that's kind of the mental model you should have for these moving forward. This is a small cartoon of what they look like. So this, if I pause it, hopefully it will be okay. This is the spectra in the radiative interior of this model. And all of these dots here, these are all representing these classical Rossby waves that we've been talking about. This lovely video that I cannot play for you because my bandwidth is clearly too small. It is showing the radial vorticity kind of beating back and forth. And if you take the spectra, you get something that looks very organized. And all of these dots are representing this dispersion relation here. So this lowest ridge, these are the sectoral modes where L equals M or lambda equals 0. They look something like this. They are the counter-rotating vortices around the equator. The next ridge up is lambda equals 1, which has one node. Then we've got lambda equals 2, 3, 4, 5, and 6, and so on. There are more Rossby waves in this simulation that are on the spectra. This is just summed over lambda equals 0 to 6, but there are many more higher order Rossby waves that are present. So the radiative interior in this model is absolutely full of Rossby waves, and they're basically the most important dynamical phenomenon happening in the radiative interior in V theta and V phi. And what I mean by that is if you take a line profile, if you take like an m equals 2 cut or an m equals 6 cut, you can see how large these modes are. So for example, this one here, this is 8 orders of magnitude above the noise floor. That is very significant. And so these things are very present, and they're probably, hopefully, doing something interesting. So just to wrap up this section, We've got Rossby waves, a lot of Rossby waves in the radiative interior, and they are, I can hear myself echoed back somewhere. Just a heads up. Thank you.
Sorry, it's my setting.
No
I
worries.
just unmuted myself for a moment to tell you that when you have a movie, you can speak and then pause the movie, or you can let the movie play and it just doesn't go along with your sound.
Yeah,
But you can have
I
the movie
know.
play and wait for like a few seconds and then pause it and then speak. Okay.
That's
Yeah,
a
yeah.
good idea. I will
Okay.
continue doing this.
Okay. Yeah, you can continue. Thank you.
Right. Um, so anyway, wrapping up this section, this is interesting for a couple of reasons. One, the fact that there are Rossby waves in the radiative interior of this model, it's not necessarily unexpected, but it does explain some things. This is the velocity profile, and the radial velocity in blue, as you would expect, decreases a lot when you go into the radiative interior because there is not convection happening. And while V theta and V phi both decrease in the radiative interior, it's not nearly as much. And part of the reason why is because there are Rossby waves going on, which are happening in V theta and V phi. So that explains this velocity. But also, if Rossby waves are the most dynamically important phenomenon happening horizontally in the radiative interior, I would hope that they'd be doing something interesting. Could they be contributing to the solar dynamo? Not sure. Could they be involved in tachycline confinement is an interesting question because they are highly anisotropic. And when you think about, I mentioned heat transport earlier, when you think about keeping a tachycline layer thin, which is in and of itself an interesting question, and Lauren's paper talks about magnetic confinement of the tachycline. If you have a highly anisotropic process right below the tachycline, one would hope that that would play some kind of role. So these are just some me spitballing thoughts, but we have lots of Rossby waves, and that is the point of this section. So on to the convection zone. We also have Rossby waves in the convection zone in this model, but there are fewer of them. So same deal with the spectra as before, but here we've got near the base of the convection zone, in the middle of the convection zone, and at the top of the convection zone. And we can see that at the base of the convection zone, all these little black dots are Rossby waves, classical Rossby waves. And we can see that we have a fair number of them at the base of the convection zone, but by the time we get to the top, there are far fewer of them. These two here that are marked are the m=2 and m=3 sectoral modes. The m=4 one is also present. And we've got a handful of modes down here that are all kind of λ=1 modes. And this is interesting because we have all these Rossby waves in the radiative interior, but we've only seen a handful of them at the surface. And so clearly something is happening in the convection zone that is limiting the number of Rossby waves that we are seeing. The final thing I want to mention is that there is a difference between the Rossby waves in the radiative interior and the Rossby waves in the convection zone that plays into all of this. So these are line profiles of the L=m=4 sectoral mode in both the radiative interior and the convection zone. And as you can see, the important thing is that they occur at different frequencies. So the radiative interior frequency one is down here, and the convection zone one is up here, and those frequencies are different. And that would only happen if there were two different families of Rossby wave living in two different cavities, a radiative interior cavity and a convection zone cavity. I'm doing some work right now. I'm doing some math right now to flesh this idea out a bit more. But for the moment, I just want to leave you with the thought that this simulation almost certainly has two different families of Rossby waves in it. And that is important when we're thinking about what we would expect to observe. So that's it for the classical Rossby wave section. We have a lot of Rossby waves in this model. They're really important to the dynamics of the radiative interior, and there's probably two different families of them going on. I'm gonna let this video play for a couple of seconds because this is kind of what the Rossby waves look like in the radiative interior in practice. So anyway, hopefully that worked. So we'll go on to the next section, which is all of the other different kinds of waves, and we're gonna probably speed through this one a little bit. So all of the spectra in this section are going to be shown in the convection zone. it's going to look something like this. We're going to be showing modes that are equatorially antisymmetric on the left and modes that are equatorially symmetric on the right, which seems backwards, but there's a reason for it. And so now we're going to get to the thermal Rossby waves. So thermal Rossby waves are also a Rossby wave in that they are also conserving potential vorticity, but the geometry is different. And so the conservation statement is different. In this case, instead of existing on a spherical shell, these waves are convective columns that are oscillating back and forth. So as you may be aware, if you've got convection that is rotating, the convective cells will align into these convective columns called Taylor or Busse columns. And if you perturb one of those columns, you can get a thermal Rossby wave. So the idea is if you push one of those columns outward, for example, that is increasing, or sorry, if you push it inwards, that is increasing the density and increasing the arc length across the sphere. That means we want to increase the speed that it is spinning to conserve the statement. That will then displace the next column outwards, which is going to decrease the density, decrease the length, then it will spin down. This will displace the next column inwards, and so on. And you get a prograde propagating wave that looks something like this video here in the middle, which is of a different simulation that I will now play. There's not much going on because the simulation is barely supercritical, but that's the general mental model, is that you've got columns this time operating in VR and VFi. So the most fundamental mode is, I'm calling it the Busse mode. Again, this is a situation where there are many different names. Thermal Rossby waves have been called banana cells, overstable convective modes, columnar convective modes. I'm going with thermal Rossby waves here, and when we're talking specifically about the most fundamental mode, which is a single row of columns around the equator, I'm calling that the Busse mode. And it has no nodes in latitude when you're thinking about it in VFi. If you go to the next latitudinal overtone, I'm calling this the Roberts mode. And this is, as you might expect, two convective columns on top of each other with one node in VFi at the equator. So these have been seen in simulations for quite a while now, but they have never been observed. Our simulation is no different. We also see them. So here on the left, we have the Busse mode. So these black squares denote values from this paper by Brad Feynman, my advisor, and his collaborator, Rekha Jain. And the thing that's very telling about thermal Rossby wave dispersion relations is they asymptote to a value that's around the rotation rate for high M, and that is absolutely what we see here. This mode is present, like I said, that's not super a surprise, but it will play into something else later. And it's being labeled by 0 because it has no nodes in latitude in VFi. If we go to the next latitudinal overtone up, we've got the Roberts mode. It looks like this. These are numerical values from this paper by Yuto Becky, who is, I think, the COFFIES Seminar speaker for next month. So that's a preview. But as you can see, this one also goes up and then it goes down and kind of asymptotes towards the rotation rate, is labeled by 1 because it's got one node in latitude because you've got two columns on top of each other. If you squint kind of hard, this is more obvious in line profiles, but you do have this ridge here, which might be the next latitudinal overtone, which would be 3 columns on top of each other. And if you squint really hard, I'm not sure I stand by this one, but this might be a situation where you have the further overtone here, where you have 4 columns stacked on top of each other with 3 nodes in VFi in latitude. So we have a lot of thermal Rossby waves, and we will have more to say about them in the final section. So the next wave that we're going to move on to is a mixed mode. So I want to establish what a mixed mode is for the purposes of this talk. I don't necessarily know the history of this terminology, but for my purposes, it's a mode where the prograde and retrograde behavior are different. And the prototypical example, at least in geophysics, is the Yanai wave. So in this diagram, we have the Poincare gravity modes here and here, and down here, all of these very close together blue lines are the classical Rossby waves from the previous section. And you can see that the pink lines are the Yanai wave, which when it's retrograde looks at something like a Rossby wave, and when it's prograde, it looks something like a gravity wave. And so the idea here is that they just have different behavior in prograde and retrograde. And I say this because the next mode we're going to be talking about is a mixed mode. So this mode was identified by Utebeki a couple of years ago, and the retrograde component of this inertial oscillation looks something like this from the eigenvalue results, eigensolver results, and in my paper is present and it looks something like this. These are the values overplotted. This mode is a little bit difficult to conceptualize. It looks kind of like the sectoral classical Rossby waves we talked about in the last section, where you have a single band of counter-rotating vortices around the equator. But rather than being a single band of counter-rotating vortices, there's definitely a radial component. And that's very interesting. So it looks something like lambda equals 0 in radial vorticity, and that there isn't a node in radial vorticity in latitude here. But clearly there's a radial component, and clearly the motions are three-dimensional. And keep that in mind, we will come back to that. But the other really interesting and important thing about this mode is that it's a mixed mode with a thermal Rossby wave. So this is the dispersion relation. We've got prograde modes in this box and this box, retrograde here and here. And you can see that if you look at the retrograde piece, it smoothly moves into the prograde piece, which is the thermal Rossby wave with two columns stacked on top of each other, or the Roberts mode. And that is also what I see in my simulation. I have another figure later on that more clearly shows that these two things do meet at m equals 0. This particular figure doesn't show m equals 0, but we will get to it. So all of this to say, we have a mixed mode between a thermal Rossby wave and something with this interesting 3D motion that is mostly horizontal at the surface, but definitely has a deeper radial component. And these two modes are mixed with each other, and it is present in the simulation. The final kind of mode I want to talk about is the high frequency retrograde vorticity waves. Like I said, the name is terrible because up until recently, we really didn't understand what they were. So I'm sure they'll get renamed at some point. But these are called high frequency because they're higher frequency than the sectoral Rossby waves that were observed. So the red line is that Rossby wave observation I pointed out earlier, and the purple line is the HFR mode observation, and it's higher frequency in magnitude. And that's why it's called this. Its characteristics are predominantly that it's anti-symmetric in radial vorticity. It specifically seems to be strong amongst a lambda equals 1. And it's seen near the surface, and its motions are 3D. And so if you're thinking about lambda equals 1, what would that mean? I know these are all 3D, but that would look like in radial vorticity, 2 rows of counter-rotating vortices with 1 node at the equator. This is just a cartoon. It will come back. I wouldn't, don't cite this cartoon, but we'll get to it. So anyway, high frequency retrograde vorticity waves, we see something that looks an awful lot like them in my simulation. So over here, we have our anti-symmetric spectra, which is what we're looking for. And this thing here is our HFR mode. So overplotted are some observations and also other numerical eigensolver results, which are all in the same general area. And that's probably what this is. We also have a symmetric band of power over here with overplotted numerical eigensolver results that saw something similar. And we have 3 other fainter bands of power here, here, and here that are all more visible in line profiles than they are on the spectra. And they all seem to be part of the same family in that they have the symmetries we would expect, and they're only seen near the surface. And so the idea is that these are probably HFR modes and associated overtones, and these are all part of the same family. So we've seen thermal Rossby waves, we have this mixed mode, and we have HFR modes and assorted overtones. So now we're going to tie everything together and say everything from the previous section is actually related to each other. We'll see how this goes. So the first thing I want to assert is that all of these things are mixed modes with each other. This is spectra and polyidal velocity, so it's a different quantity, and it's presented slightly differently to make mixed mode relationships more clear. So we have, instead of showing the prograde motions with positive frequency and positive m, we're showing them a negative frequency and negative m. So that's basically like in this diagram from earlier, we were showing like these 2 squares, and now we're showing these two squares. So it's the same information, just kind of tipped over. And so, for example, this here is the Blume thermoroscopy wave with one column from earlier. It's just been tipped over. And this here is the mixed mode that we were talking about 2 minutes ago. We've got the Roberts mode here, and it smoothly moves into the retrograde branch from earlier through n equals 0. But the other thing that's interesting is that if you look at this next branch, you can kind of see that the retrograde piece seems to meet what is most likely a thermoroscopy wave overtone, or the thermoroscopy wave with 3 columns on top of each other. And so that would mean, and this here is the HFR branch, that would mean that the HFR modes are also mixed with thermoroscopy waves. And that may or may not be true with the other overtones that are present, since those are much lower in magnitude. So my first assertion is that the HFR modes are mixed with thermoroscopy wave, and also because of that, that they are of the same class as this other mixed mode that was previously identified. And this is all generally part of a class of modes that have prograde thermoroscopy waves and this kind of retrograde 3D quasi-vortical behavior. So all of these things are related. What is it? Is then the question. So this section, because I'm at a point in my understanding of this where it's still a little bit new, I'm going to present this information in the way that it was revealed to me, which is probably not necessarily the best way for pedagogy. If you talk to me in a couple of months, I'll probably have a different and better way of explaining it, but this is what I have for right now. So while I was looking at all of these simulation results, for the past couple of years, my advisor, Brad, and his collaborator, Reka, have been working through thermal Rossby wave related mathematics. They've been slowly building up their understanding about how thermal Rossby waves exist in different environments, both stable, neutrally stable, and unstable, and trying to understand, slowly build up everything. And they did a calculation where they allowed latitudinal propagation for their thermal Rossby waves. And this is interesting because thermal Rossby waves, when you think about them, you can think about them kind of as latitudinally invariant. They seem to be, they're columns that exist in radius and phi, and you don't really necessarily have to think about the variation in latitude. But if you allow propagation in latitude, you get this term. So in this wave number, this left term gives you prograde thermal Rossby waves that we know and love. The right term gives you internal gravity waves, and this middle term is new and arises from the latitudinal propagation, and it gives you a retrograde branch. So this here is a figure from, I think, this paper up here, and this is showing the resulting dispersion relation from these terms. So ignore the dots. The first thing we're going to look at are these solid lines. These are our prograde thermal Rossby waves. This here is the Blume mode. This is the Roberts mode. This is the next overtone, etc. And this is as expected. When this term is added in, you get the retrograde branch, and these retrograde branch connect to all of the lines with the corresponding colors above, and that will be more obvious in a later figure. But because of this, we now have a retrograde branch that looks suspiciously similar to a lot of the retrograde waves that we've been looking at. So we've got HFR modes, we have this retrograde mixed mode, and it at least is qualitatively similar. And so this is potentially the beginnings of an explanation for what all of these waves are, what the HFR mode is, what that other kind of not fully understood retrograde mixed mode is. This is the beginning of that. And that is a very confusing statement. So basically, we've found potentially analytically an understanding of what these mixed modes are, which explains a lot of the things that we've seen in simulations and in observations, and latitudinal propagation seems to play a role in all of this. But that's still confusing. So I have a kind of dumb PowerPoint cartoon that I will probably end up updating in a couple of months. So first, a reminder for all of the retrograde pieces, or the retrograde pieces that we care about. The first one is, first mixed mode that looks like this, and is lambda equals 0 radial vorticity, and kind of looks like a single band of counter-rotating vortices at the equator. When you look at the HFR modes, they're also 3D, they're lambda equals 1, and they're 2 rows of counter-rotating vortices with a node at the equator. the thermal Rossby waves that we care about, we've got, for the Roberts mode, which we know is mixed, 2 counter-rotating columns on top of each other. And then we have, with 1 node in V phi at the equator. And if you go to the next overtone, you have 3 columns stacked on top of each other with 2 nodes in V phi in latitude. And if we overlay these dumb PowerPoint cartoons, I'm asserting basically that the retrograde piece are boundary modes of the thermal Rossby waves. So if you've got 2 counter-rotating columns on top of each other, as we do here, something is going to be happening at the boundary. You aren't just going to have 2 happily rotating fluids. There's going to be something interesting happening there. And the thing that is happening there is the retrograde piece. And similarly, if you've got 3 columns on top of each other with the thermal Rossby wave, you've got 2 places where there's a boundary. And with the HFR mode, you have 2 rows of this quasi-vortical structure. And so the idea is that this retrograde piece of these mixed modes are the boundary modes for the thermal Rossby waves. That is not a complete explanation. This doesn't explain necessarily intuitively why they're retrograde, why they have to be retrograde. I don't fully understand, for example, like how you would get like a wave guide from these thermal Rossby waves. I'm still very much figuring this out, but this is, I think, a helpful cartoon in understanding how these different pieces match up with each other. The one that last thing I'd like to note is that some of you who are probably more well-versed in the fluids literature than I am have potentially noticed that this term here, this 4k squared omega squared term, seems familiar, and that it's basically from the Poincare equation, and you would be right. So I mentioned at the very beginning of this presentation that inertial oscillations as a category is a relatively recent usage of the term, as far as I can tell, and that they originally meant a very specific kind of wave, and this is the very specific kind of wave that they were referring to. So the Poincare equation is inviscid, incompressible, kind of the most simple physical thing you can think about when you're thinking about rotation. It's also a mathematically very ill-posed problem, and it's a hyperbolic equation. It's very difficult to solve. I know there were full sphere solutions, I think, in 1888, but spherical shell solutions didn't come around until the 90s. So it's mathematically annoying, and you get an inertial wave path that looks something like this, which is very strange. But evidently, in a cylindrical geometry, the solutions look a little bit nicer, and we've kind of rediscovered this inertial, or it's come up in the math, this inertial mode component when doing this calculation, because this calculation was done in a columnar geometry for an anelastic situation. And so what we're seeing here is this combination of your thermal convective modes and also these very original inertial modes that have been an object of interest for a very long time. And I just want to end by saying that there is plenty of geophysical literature that does talk about this that I've been diving into. Science has, I think, as many human organization problems as it has technical problems. I think this is an example of concepts that have been thrown around for a while in the geophysical community that are definitely applicable to the solar community. And so this will definitely be guiding a lot of the follow-on research to this concept as we try and understand what all these retrograde waves that have been showing up in models and observations are. So to tie everything together, this is an image adapted from a paper that was released recently, a couple of months ago, that basically just says, here are all of the different models and simulations and how they tie into this analytical mathematics that has been done. So we've got our Busse mode here, our Roberts mode, the mixed inertial piece, this is the HFR mode, etc. And all of this is just saying that we have a class of mixed modes. The prograde branch are thermal Rossby waves, the retrograde branch are these 3-dimensional boundary modes that we're still trying to understand. And so to fully tie things together, we can rewrite this lovely image and we can replace it with this. So we've got our classical Rossby waves, our high latitude modes, and our critical latitude modes from before, and then everything else is a mixed mode. And that makes it a little bit easier to parse some of the recent results. So that brings it to the end of my presentation. We have a lot of Rossby waves, we have a lot of mixed modes, and there are 2 papers that talk about this if you want more detailed and less internet spotty explanations. And I will now take questions.
Thank you, Catherine. Wonderful talk. Thank you, Catherine. I see already some discussions in the chat.
Oh,
Do people want to repeat the questions in the chat? If not, we have raised hands also. So, Sasha, you have a question?
Yeah, thank you. Thank you for the very interesting presentation. And properties of inertial Rossby waves, they crucially depend on stratification, particularly on Brunt-Väisälä frequency. So I'm wondering what is stratification in your simulations?
I'm sorry, can you repeat? My internet decided to be annoying.
Yeah, the properties of inertial Rossby waves
Yes.
crucially depend on stratification,
Yes.
in particular on Brunt-Väisälä frequency.
Mm-hmm.
And what's your Brunt-Väisälä frequency in your model?
I don't think I have a figure prepared, but it's something on the order, in the radiative interior, it's something on the order of hundreds of microhertz. So it's very well separated from the inertial range. And then in the convection zone, it's very, very small.
Was it stable or what? Because you didn't include any surface shell layer.
It's quite similar to what it would be from a solar model. So
so you have convection and that, because it depends on the ratio of Brunt-Väisälä frequency to rotational frequency, and on the sun there's transition somewhere in the middle convection zone where it goes through unity, and that's what causes these effects of mixing and all these.
Okay, so in the radiative zone, it's quite similar to what we'd expect from a solar model.
Right, yeah, I understood. But what is the convection zone?
Yeah, when the convection zone, we don't really control for, well, we can't, because that's determined by the convection itself.
But you can measure it, right?
Well, not
I've got.
Yeah, this
I
was.
have a plot. I just don't have one in the slide deck.
Yeah, I would recommend you to look at my old papers with Zimbowski, somewhere in that what we developed complete theory, including these wave guides for Rossby inertial modes, and not in local dispersion relation, but in full spherical approximation.
Yeah, that would be
also
really
we have prograde, retrograde modes. I can put in chat this link.
Yeah, perfect. Thank you.
Okay, next question from Gustavo.
Hi, Catherine. Thank you very much. It was very nice. Regarding the last part of your talk, it was very interesting how you tried to put everything together in one model for explaining all the branches of waves. But what is confusing me is if these waves are part of the same, all should appear, right? Why we don't see the thermal Rossby waves and we do see very clearly the high frequency modes?
That's a great question. I wish I had a simple answer for you. So the model that we have is not exactly the most physical thing, the analytical model. It was done kind of in a big cylinder, and it's anelastic, and all of these things are very sensitive to, in our case, compressional beta effect. And so I mean, honestly, it could be any number of reasons. And also, why haven't we seen thermal Rossby waves? So yeah, I wish I had an answer for you. Like I said, my understanding of this is very new. And so I'm hoping to have more answers, definitely by the time I defend in a couple of years. We'll get there.
Thank you.
Okay, any more questions? Oh, okay, Tom has one.
You have to unmute us.
Well, I hear Todd, but I can't hear Tom.
Okay. Do you observe G modes in your simulations?
Yes, there are G modes in the radiative interior. They're very well separated from all the Rossby wave stuff. Like I said, they're kind of in the microhertz range, or like hundreds of microhertz range. Because this is an elastic simulation, they're also kind of wrong, which is why I didn't show them here. But they are present. They're just not interacting with the Rossby modes in any way that I can see.
Thank you.
Okay. Okay, if we don't have other raised
I
hands,
had a
but
related question, I think, although it was about some of the conversation in terms of tachycline confinement. That was
Oh, well, you can happily direct those questions to Lauren.
okay. I do see a continuous discussion in the chat. Does anyone want to bring this to speaker, or has anyone already got all question answered in the chat already?
Most of what I was putting in the chat were some like explanations for, you know, some of the students who are newer to these concepts, but a lot of the discussion that sort of started was about the tachycline confinement, and about how tachycline confinement is probably caused by Smurfs, according to Nick Featherstone.
I have a question to Catherine related to tachycline confinement.
Sure.
Could the Rossby waves transport angular momentum? Do they transport angular momentum in the radiative zone in any of your models?
I looked a long time ago, so I need to look again because I understand things much better now. I remember when I looked like a couple of years ago at this point, I remember it seemed to be mostly heat transport related as opposed to angular momentum transport. But also I did not understand things well then. So it's definitely something I would like to look at again.
Yeah, because the gravity waves, I mean, that was like an early theory, not really based on simulations of that I never really understood, but sort of nonlinear gravity wave breaking. But now we've got Rossby waves, and they seem to be a lot stronger potentially than the gravity waves. So maybe that's like even another way.
That's definitely a thought. I remember the Reynolds stresses being really strong though, so we'll see. It wouldn't take that much effort to look, so I should probably just do that.
Okay, we are at an hour now, so wonderful talks, very, very clearly explained and very well prepared. Thank you, Catherine, and thank you for the nice discussion in the chat and after the talk. Thank you all for attending our seminar. As Catherine has mentioned, our next speaker is YouTube Betty, so she kind of make a focus of that. So hope to see you all next month at our next COFFIES seminar. And let me bring back the poem website again. So if any of you are interested, please go look at the poetsforscience.org website, and the submission is still open. So if you are interested, go show some nice work of modern poems, so you're interested. Okay, that's all. Thank you to our Catherine and all the attendees today.
Thanks so much. Sorry for the internet troubles.
Oh, no worry. Thank you for giving the talk in France. It's very across many time zones, and we are not expecting the bandwidth thing, but thank you for making it happen. Bye.